So in the previous classes we have discussed all about the close packing. Okay, so we can actually conclude the previous classes, that means about the close packing like this one. Okay, so let's suppose this is your close packing. Okay, so close packing can be actually categorized, or we can actually systematize this one like this. The first one is actually one dimensional, okay, and the second one is your two dimensional, and the third one, which is very important, is what? Three dimensional. Okay, so we know that for one dimensional the constituent particle will going to fill up along one axis. Okay, so this is actually axial arrangement, or that means one dimensional arrangement. Okay, and the second one is the two dimension, in which the constituent particle will going to arrange in a plane, or they will going to form a layer. Okay, so it will be a plane. Okay, so it will going to form a plane or a layer. But in case of this three dimensional, this is very important, because the all solid crystal will actually exhibit three dimensional structure or three dimensional close packing. Okay, so it will be actually your the packing will be along the x, y and z directions. That means this is the three dimension. Okay, again in case of the two dimension, we have actually two types of arrangement. On the basis of the arrangement of the constituent particle, we have two types of packing. Okay, the first one is actually square close packing. Okay, square close packing, and the second one is what? Second one is your two dimensional hexagonal close packing. Never forget to write this 2D, okay, because if you don't write this 2D, only if you write hexagonal close packing, then it will be wrong. Okay, because we have also hexagonal close packing in case of 3D also. Okay, so that now coming to the three dimension, this is very important. Okay, three dimensional, again we actually classified the three dimensional packing on the basis of the arrangement of this actually square close packing and hexagonal close packing, or in other words we can say that we basically use these layers. Actually this is the layer, no? Square close packing is a layer, and also the two dimensional hexagonal close packing is also a layer. Okay, so we're going to use this layer, and on this layer or on the top of this layer, we'll again going to add another layer of that that packing. Understand? That means we're going to use one layer of square close packing, again on the top of it, again we're going to add another square close packing, again another square close packing layer. So we're going to get some three dimensional structure. Okay, so on the basis of this actually layers, so we have what? Two types of layer now. One is square close packing layer, and another is what? Two dimensional hexagonal close packing layer. So we have mainly two different types of three dimensional close packing on the basis of this layer. So in first case we're going to use only the square close packing. Okay, so if we use the square close packing one layer, then again we add another square close packing layer on the first layer, again we're going to add third layer on the second layer. The sphere of the second layer is exactly actually exactly over the first layer sphere, or the third layer sphere will exactly over the second layer sphere. Then it will going to give you that simple or primitive type of unit cell structure or close packing. Okay, so the first one is actually is obtained by placing the second layer over first layer. Okay, first layer. And actually in this case we have two types of voids. Okay, when we place the second layer over the first layer, then we get two types of void. The first one is tetrahedral void and the second one is octahedral void. Okay, so this is the first case, that means the placing second layer over the first layer. But again we can place the third layer over the second layer, okay, by covering the tetrahedral void. That means by covering, actually we place the third layer such a way that the sphere of the third layer will going to on the top of that tetrahedral void in one case, and the second case we will going to place the sphere of the third layer covering this octahedral void. Okay, so we have two types of 3D packing. Okay, so the first one is actually it will going to give you the SCP, that means hexagonal close packing structure. Okay, and the second one, when we cover the octahedral void, then it will going to give you CCP, that means cubic close packing. Okay, or you can say FCC, that means face centered cubic packing. Okay, face centered cubic lattice, actually cubic unit cell. You will going to get that face centered cubic unit cell from this CCP CCP packing. Understand? So this is all about this close packing. So from the study, actually we also have the idea about the number of voids, how many number of voids will be present in case of the 3D close packing. So we able to know that actually from the previous class we have the information that for the three-dimensional packing, for this placing the second layer over the first layer or placing the third layer over the second layer, we have actually, we know that if the number of constituent particle is n, if the number of constituent particle is capital N for any one of this one, okay, any one, it may be SCP, it may be CCP, okay, if the number of constituent particle is n, then the number of octahedral void will always equal to capital N, and the number of tetrahedral void is equal to twice n. Okay, so we have this information now. Okay, and again we have another information, which is what, the coordination number for any of this one. It may be SCP, it may be CCP. Okay, anyone is always 12. That means the coordination number for the SCP is equal to 12, also the CCP is equal to 12. Okay, why? Because actually if you see this figure here, if you see this figure, then you are able to know that here the one constituent particle is surrounded by neighboring how many particles? 12 particles. You see, 1 2 3 4 5 6 7 8 9 10 11 12. Okay, understand? So it is for this SCP, and the CCP also same. You see, this is the one constituent particle, and this constituent particle is covered by total 1 2 3 4 5 6 7 8 9 10 11 12. Okay, 12. That's why the coordination number is 12 for both the cases. Okay, so now what is our aim? The aim of this class is to actually find out the the formula, molecular formula of that crystal, solid or solid crystal, by using this data. Okay, so let us now discuss in detail about how to calculate how to find out the molecular formula by using this data, which is actually studied in the previous classes. Okay, the objective of this class is actually to calculate the formula of a compound and number of voids filled. Okay, and number of voids filled. So this is actually the objective of this class. Okay, understand? So now, before going to actually calculate the formula, we need to know some concept. Okay, So the first concept is actually the concept. Okay, so we have to know some concept. So please remember this concept. Okay, so the let's suppose if the solid is a ionic solid. If the solid is an ionic solid, then what will going to happen? So we know that for ionic solid the constituent particles are what? Ions. That means the positive, that means cation and anion. Okay, so N, that means this is what? This is your cation and this is your anion. Okay, anion. So again, one more important point is that always remember this point. Okay, that the size of anion is bigger than cation. Always remember this point. Okay, so the size will be of the anion is always bigger than cation. So why? What is the reason behind this? The reason behind it, actually we can understand the reason by taking an example. Okay, so let's suppose we have the sodium chloride crystal, the ionic solid. Okay, so it has sodium positive and chloride negative constituent particles. Okay, so here to understand this phenomenon we need to know about their electronic configuration. So what is the electronic configuration of element sodium? The element sodium electronic configuration is actually 1s2, 2s2, 2p 6 and 3s1. Okay, so this is the electronic configuration of sodium, and electronic configuration of chlorine is actually the electronic configuration of neon into 3s to 3p5. Okay, so now we know that let's suppose you can represent the electronic configuration this way, no? So this is the, suppose this is the nucleus and this is the first cell. So in the first cell, suppose this is for sodium. Okay, 2 electrons will be there. Second cell, 2 electrons will be there, twice as. Third cell, again how many? 6. 1, 2, 3, 4, 5, 6 electrons will be there. And the fourth cell, which is the TS, actually it will have 1 electron. Okay, okay, so this is actually the representation of the sodium element. Okay, so when we remove 1 electron, then it will become what? Sodium positive. Sodium positive. Okay, so 1 electron is going to be removed. So the thing is that when we remove that 1 electron, here you see, then what will happen? That this outermost cell will going to vanish. So if this is vanished, then the size of the positive ion will become small. Understand? And this is the first factor. And the second factor is that if let's suppose you are pulling 2. So here let's suppose this is you are actually pulling 2 bags. Okay, heavy bags. So if you are given only 1 bags, okay, instead of 2, then you can pull the 1 bag more closer to you than the 2 bags. Understand? So like this, actually here you see this is the positive, no? This positive nucleus. So this before the removal of that electron, it will actually this nucleus is actually pulling how many electrons? Total 11 electrons will going to actually 11 electron is pulled by this positive nucleus. You see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so and after removal of 1 electron, the same nucleus will going to pull 10 electrons. Okay, that means it will going to pull more closer in case of that sodium positive. That means in case of sodium positive, the nucleus can pull more towards the electrons more towards the positive ion, that means the nucleus. So the size of the this sodium positive will be smaller than the size of the sodium. So this is the 2 factor. And similarly in case of chloride, that means Cl negative, it will become what? First of all, this is chloride. The electronic configuration of chlorine is neon 3s2 3p5. Okay, but the electronic configuration of chloride will be what? Neon 3s2 3p6. That means 1 electron will be more. So that means we have to introduce 1 electron to the chlorine atoms. Okay, so if 1 electron will be more, then then here by using this analogy we can say that the size of the Cl negative ion will be higher than the chloride. Okay, so that's why always remember this point, that the size of anion is always bigger than size of cation. Okay, so this is one concept. Okay, now the question is actually why we need this concept. Okay, so we know that in case of 3D packing, it may be HCP or CCP. Okay, there are two types of voids, okay, which are tetrahedral voids and octahedral voids. Okay, so moreover, since the size of the anion is bigger than the cation, so the anions will going to form the packing structure, and the cation will present in the voids. Understand? So that means the packing will going to form by the anions. So these packings, or this sphere will be your anions. Okay, in case of that ionic solid, the sphere will be your anions, and the voids, this tetrahedral voids or the octahedral voids will be occupied by the cations. Okay, because of their smaller size. Okay, if the size of the cation is very small, okay, then they will occupy the tetrahedral voids, and if the size of the cation is slightly bigger, then they will occupy the octahedral voids, as the octahedral voids are bigger than the tetrahedral voids. Okay, so that means we are able to know that the tetrahedral void is actually the size of the tetrahedral void. Okay, size of tetrahedral void is smaller than the size of octahedral void. Okay, octahedral void. Okay, so this is also one important point. Clear? So that I always remember that all the voids may or may not be occupied by the all cations. Okay, and this is actually depends upon the formula of the the compound. That means this if there are let's suppose the formula of the XY. Let's suppose the formula of the ionic compound is XY. Suppose there are only 2 cations here and 5 anions there. Okay, so that means there will be 5 constituent particles. Okay, that means 5 sphere will be present, but we know that 5 that sphere will going to form 5 octahedral void and 10 tetrahedral void. Do you understand this point? So let's suppose this is your formula. Okay, this is your formula of the ionic solid. Okay, X2, where X is the cation and Y is anion. Let's suppose. Okay, so we know that the anion will going to form that packing structure. That means the anion will be here, the sphere will be the anion. Okay, understand? And the cation will be present in what? In the void, inside that void. Okay, so we know that if the number of sphere is 5, then the number of octahedral void will be also 5, and the number of tetrahedral void will be twice into 5, because we already know that if the number of the sphere will be n, then the octahedral void will be capital N, the tetrahedral void will be twice n. That's why this one. Okay, so here we have total 5 octahedral void and 10 tetrahedral void, but we only have how many cation? Only two cations. So only 2 cations will going to occupy only 2 tetrahedral void or 2 octahedral void, depending upon their size. Okay, if the size of the cation is slightly bigger, then it will going to occupy the octahedral void, and if the size of the cation is small, very small, then it will going to occupy the tetrahedral void. Okay, and that means what we understand that all the voids are not occupied by the cations. It may occupy, but it will depends upon what the formula of the compounds. So now let us find out the formula of some compounds by using these concepts, by using some examples. Okay, mainly two examples we're going to use. Okay, now let us discuss about some examples. Okay, so the first example is actually 1.1. I am taking the example from your NCERT book. Okay, so here the actual example is a compound is formed by two elements X, Y. Okay, and the atoms of the elements Y make CCP. That means the anions. Okay, CCP 3D packing, and those of the element X as cation occupy all the octahedral voids. What is the formula of the compound? So we have to find out the formula of the compound. Okay, so what is given? The given thing is that, so they said that the compound is formed by the two elements. So that means X and Y. So we have the two elements which are X, Y, and here they said that the Y is actually going to form that packing structure. That means packing structure which is CCP. That means the CCP cubic closed packing structure will be formed by that Y. That means Y is what? Y is actually anion. Anion, because we know that anion will going to form the packing structure. Okay, so and X is what? Then X is your cation. So X is cation. So anion is your Y and cation is X. Okay, so again they said that the element X occupy all the octahedral voids. So they said that X occupies, actually all the X occupy all the octahedral voids. Sometimes we represent octahedral as OH. Okay, octahedral voids. But in exam write properly. Okay, octahedral, not OH. So the X occupy all the octahedral voids. What is the meaning of it? That means X will going to occupy all the octahedral voids, means the number of X will be what? Number of X will be actually the number of X is equal to what then? Then number of octahedral voids. Okay, octahedral voids, because it will going to occupy all of them. Understand? So again we know that number of octahedral voids is actually equal to what? Number of octahedral voids is equal to actually your number of spheres which form the what? Which form the packing, structure. Okay, so here number of sphere which form the packing structure is what? The number of anion, because we know that number here we know that the packing structure will be formed by the anion. So here actually they will be going to form the packing structure. Okay, packing structure will be formed by the anion. We already know this one. So the number of anions is equal to the number of sphere which is from the packing structure, actually which is equal to the number of octahedral voids. Understand? So actually this concept is used by which concept? By using which concept? This concept, the number of sphere present is 1, then the number of octahedral void is capital N, the number of tetrahedral void is twice N. So here we use this concept only. Okay, so here number of anions. So we know that number of, that means what we can say? That means the number of anions equal to number of X is what? Cation. That means the number of cation. Understand? So this is your actually number of X is what? Number of cation. Okay, clear? So we able to know these things. Number of cation is equal to number of anion. That means the ratio will be what? 1:1. If number of anion will present 1, that means if the number of anion is 1, then the number of cation is 1. If it is 5, this is 5. If number of anion present in that solid is 10, then the number of cation also will be 10. So that means here our formula will be what? X1, Y1. Or we can say that the compound for the formula of the compound, or you can say the solid, okay, is equal to what? Is x, y. Understand? Because the number of cations is equal to number of anions. So now let us discuss about the second example, okay. So now coming to the example 2, which is example 1.2, okay. So this example is also taken from your NCERT book, okay. So according to this example, atoms of elements B form HCP lattice, and those of the element A occupy 2/3 of the tetrahedral voids, okay. What is the formula of the compound formed by the element A and B, okay. So here they said that the atoms which are present are, that means 2 atoms are present which are A and B, okay. So elements, that means the elements present in the, okay, in the compounds are what? A and B, okay. But here again they said that B form the HCP lattice, HCP lattice. So B form HCP lattice means what? That means this will going to form the what? The packing structure. That means, that is, we can write that B is actually anion, okay. B is the anion, okay. And again they say that A occupy how many? 2/3 of the tetrahedral voids. Total, if the total number of tetrahedral void is capital N, then 2/3 of that voids will going to occupy by the A. So A is what? A is actually your cation. Understand? So let us suppose the formula of the the compound is AXBY, okay. Suppose this is the, let us suppose the formula of the compound is AXBY, okay. So here they said that the A will going to occupy 2/3 of the tetrahedral voids, and we know that the tetrahedral voids will be what? If let's suppose the number of B, that means the anion present in that compound is Y, okay. Understand? Y. That means if the number of anion is Y, then the number of tetrahedral void will be what? So if the number of anion will be Y, then we know that then the number of tetrahedral void is equal to what? 2y. Because, why 2y? Because we know that if it is n, then it is 2n. We already discussed this in the previous example, okay. And also the previous concept, we already know that if okay, we know that if the number of sphere is equal to n, then the number of tetrahedral void is equal to what? Twice n, and the number of octahedral void is what? N. Okay, so here let's suppose the number of anion is y, because that's why we here write here y, okay. Y, then it will be number of sphere will be y, then tetrahedral void will be twice y, so we write twice y, okay. And since the only 2/3 of the tetrahedral void will be occupied by the A, so the number of A will be what? Number of atom A will be is equal to actually 2/3 of that tetrahedral void, na? So tetrahedral void, number of tetrahedral void is what? This one, twice y. So 2/3 of tetrahedral void, that means this one. So the number of atom A present in that compound is equal to 4/3y. Understand? So this is the number of atom A present in that compound, and the number of we already consider here what this is y actually what this is actually number of b, okay, number of b present in that compound, okay, in that compound. So number of b present in that compound is y, and number of a present in that compound is equal to 4 by 3y. So thus the molecular formula will be that formula of the compound, the formula of the compound is equal to what is a in place of x, what we can write, because this is the number x represent what number of atom A, okay, or number of cation A. X represent number of cation, okay, that means this number of A is actually this is x, okay, so x is equal to 4 by 3y, so we can write here 4 by 3y, and here by, so y we can multiply by 1 by y. So if you multiply by 1 by y, then what we'll get we'll get the formula as A4B3. Understand? If you multiply by t by y, if you multiply by t by y actually, then we get this one. So our that means the molecular formula or the formula of the compound is actually your what A by A4B3, okay. So that's what we can write. Thus the formula of the compound of the given compound is A4B3. So this is the answer, okay. So hope you understand. So in the above two example 1.1 and 1.2, we actually we used the concept of this concept actually. If number of sphere is, that means the sphere which will going to form that packing structure is equal to n, then number of tetrahedral void is twice n, and number of octahedral void is n. So we just use this concept and also use the information which is given in that example, okay. And by using this information, we can easily solve this type of problem, okay. So hope you understand, and try to do this type of problem. You can find this type of problem in any competitions book, okay. Also I will give some problem after finishing this chapter, okay.